Good morning, everyone. My name is Lynn Tesh. I'm the director of the High Resolution Mass Spectrometry Facility. We are a research core facility supported by the Office of the Vice President for Research. We are housed in the chemistry building on the ground floor in room W76. The other staff member is Vic Parcells, and here is our our contact information. The services we provide, we mainly focus on small molecules, mass spectrometry of small molecules, so GCMS, LC-MS, and tandem mass spectrometry, or MSMS experiments. What's unique to us is we train users on the instrumentation, and we also help with method development. We have a number of users on each of the instruments, and we're happy to help you with your questions and your projects. Just to name a few of the services, with qualitative analysis, we're looking at exact mass measurement, or what is termed now high resolution accurate mass, or HRAM, purity, discovery and identification, and then for quantitative analysis using mostly MRM, multiple reaction monitoring, we can do drug metabolism and pharmacokinetics, and we've done a lot of we've done some environmental trace analysis with some groups. Just recently, we installed a Thermo Q Exactive. It's an ultra high resolution mass spectrometer with a Vanquish UPLC. And also about the same time, we installed a new triple quadrupole mass spectrometer for quantitative analysis, and this is a Waters Zevo TQS Chronos. And then our other two instruments are a GCMS, a high resolution GCMS. It's a GC time of flight Premier from Waters with an Agilent 7890 GC. And the other instrument is a high resolution LCMS, and it's a Waters QTOF Premier with an Acuity HPLC. Just to give you an overview of all the instruments, here are the instruments. We have a variety of different mass analyzers, mostly LC with one GC system. Two of the LC systems have UV detectors. And here shows the resolution, and we go anywhere from unit resolution with the triple quad all the way up to 140,000 resolution with the Q Exactive. We don't normally run at 140,000 resolution, but we do run normally at 70,000. And the addition of this instrument really boosted our resolution capabilities and our mass accuracy. And here's a listing of the approximate mass ranges that we can work with. But if you know anything about electrospray, you know we're detecting things in M over Z, where Z is a charge state, so we can do things like myoglobin within that 4,000 mass range or less by adding a number of charges, reducing the effective mass of the protein. And just to give you an idea about resolution, so this is two nominally mass similar compounds, N-acetyl-ornithine and arginine, and you'll see at 15,000 resolution, we're barely noticing that arginine is there, but as you continue to increase resolution, we eventually get to baseline resolution and better. And so this will really help identify unknowns and multiple components. There's a trade-off for that high resolution in the scan speed. So scan speed is important when you're trying to do quantitation. So you want to get as many points across the peak that you can get without losing all the other things that could be eluting at the same time. So that's where, so here's 30,000 resolution. Notice the number of points across the peak reduces at 60, and then when we go up to 120K, we've really reduced the points across the peak. So there's the trade-off that we have to consider when we go to the ultimate resolution. But on the other hand, this is kind of cool. As a mass spectrometrist, I kind of geek out about this. Normally on the QTOF that we've had, we can see the M plus H and then the C13 and 2C13 ions. But now with the Q Exactive, we can zoom in and see the fine structure where we can see the other isotopes that like deuterium or sulfur 33 or N15. I think that's kind of nice. So mainly the thing that makes the mass spectrometers that we have more powerful, at least the LCMSs, is that we can do MSMS with triple quads for quantitative analysis. Yes, it's low res, but it's also very sensitive and it has a pretty high degree of specificity. The QTOF, it has high resolution, a slightly narrow dynamic range, but it can still do discovery and HRAM. But with the Orbitrap, we kind of really expanded our capabilities. By now we have the ultra high resolution, we have a wider dynamic range, so we can use it for discovery, HRAM analysis or measurements. And what's really unique is we have a qual-quant all-in-one workflow with that instrument. Just to give you an idea of what I mean by MSMS, usually you have multiple mass spectrometers. In each of these cases, we have a quadrupole and then a mass analyzer, whether it be another quadrupole, a time of flight, or an Orbitrap. So the MS1 is for just doing product ion scanning or daughter ion scanning. The MS1 is fixed for that parent, then it's collisionally induced dissociations, and we collect all the daughter ions. When we're doing quantitative analysis, we want to select a particular daughter ion. So we do what's called selected reaction monitoring. So we, again, MS1 fixes the parent ion, we fragment it, and then we look for very specific daughter ions to that parent ion, which gives the triple quad its specificity. We can also do this with the Q Exactive. They just have slightly different names. The other type of tandem mass spectrometry is called precursor ion scanning. So if you have a daughter ion, like the loss of a sulfate or a phosphate or a glucose ring, we can then translate that back to detection of that daughter ion to what in MS1 produced that daughter ion. And we can get the precursor or parent ion of that. So to give you an example, so the pharmacokinetic study, which is quantitative analysis using multiple reaction monitoring or MRM, here it shows the chromatogram. We have the MRM for the drug, the internal standard, and then 2 of its metabolites. And then we can print out reports that shows a table of the area counts and how it came to create this calibration curve for M1, M6, and the drug itself. And then another example is that we looked at the degradation of doxorubicin, and we used LC-UV-MS initially to look at the oxidized and untreated samples. Then we looked at the positive and negative full scan data, and then we went a step further and collected the MSMS of the metabolites that we saw. And then to confirm those metabolites, we went to authentic standards to confirm retention time, parent ion, and daughter ion fragmentation. And here's the UV chromatogram for the untreated and inactivated or degraded doxorubicin, and the two metabolites that we found. And here we have on the lower ones the MS, the full scan of the metabolites, and then their MSMS, and we were able to get authentic standards with these again and provide confirmation of identity. We can also do discovery using LCMS and LC-MSMS. Here's an example of using urine for measuring gentamicin dosed mice and what's in their urine. So we're kind of looking at a small metabolite study. And here it shows the LCMS of the positive ion and then the negative ion mode. And we were able to detect multiple different types of compounds and see the full changes once you take the data into a third party. In this case, we used a third party software, online software to do that. And we were also able to identify an unknown by going back, looking at its MS spectra here, and getting with that third-party software, getting a punitive identification, and then coming back with an authentic standard to confirm its identification. That's all I have for today, and I appreciate your attention, and I look forward to any questions that you might have in your in the Q&A session.